Imagine a material so slippery that nothing can grab hold of it. Not even a gecko's feet can find purchase on its surface. This is polytetrafluoroethylene, better known as PTFE. It is one of the most slippery solids in existence, a chemical marvel that seems to defy the laws of friction. But this creates a massive engineering paradox. If nothing can stick to PTFE, how on earth do we get it to stick to a metal frying pan? This is the story of bonding the unbondable. It's a process that requires moving from the massive scales of industrial foundries down to the molecular level, where atoms are literally forced to change their behavior. To build a nonstick pan, we don't just paint a surface, we engage in a high-stakes battle of physics and chemistry. From the raw aluminum discs to the final high-temperature sintering, every step is a feat of precision engineering designed to ensure that your morning eggs slide off with zero resistance, while the coating stays locked onto the metal for years of heat and wear. Today, we go deep into the factory floor to witness the transformation of sand and chemicals into the ultimate kitchen tool. Every nonstick pan begins its life as raw aluminum. Engineers choose aluminum because of its incredible thermal conductivity. It's second only to copper in common cookware, but much lighter and more affordable. The process starts with massive slabs of aluminum alloy, which are fed into heavy-duty rolling mills. These rollers apply millions of pounds of pressure, flattening the metal into precise sheets. Then, a high-speed blanking press punches out circular discs called slugs. For high-quality pans, we use a process called impact bonding or cold forging. A massive hydraulic press capable of exerting over 3,000 tons of force slams down on the aluminum disc. This doesn't just shape the pan, it densifies the molecular structure of the metal, making it stronger and less prone to warping under high heat. The result is a blank, a perfectly shaped vessel ready for its chemical transformation. But even though the surface looks smooth to the naked eye, it's far too slick for the PTFE to grip. To make the unbondable stick, we first have to destroy this smoothness. We are about to turn this polished surface into a microscopic mountain range. If you tried to glue PTFE to a smooth piece of aluminum, it would peel off like a sticker. To solve this, engineers use mechanical interlocking. The first step is grit blasting. Inside an airtight chamber, high-pressure nozzles fire microscopic particles of aluminum oxide at the pan's surface. Think of it like a localized sandstorm moving at hundreds of miles per hour. Each particle acts like a tiny hammer, cratering the surface and increasing the surface area by over 400%. This turns the smooth metal into a rugged landscape of peaks and valleys, invisible to the eye but essential for what comes next. Next, the pans undergo a chemical etch. They are submerged in an acidic bath that eats away at the metal on a molecular level, creating deep pores and undercut grooves. This creates a hook system. When the liquid coating is later applied, it will flow into these microscopic hooks and solidify, physically locking the plastic to the metal. It's not a chemical bond yet, it's a mechanical anchor. But metal and plastic are still natural enemies, and to bridge the gap, we need a secret middleman material. Now we enter the most critical phase, applying the primer. This isn't just paint, it's a sophisticated hybrid material. The primer contains a mix of PTFE particles and high-strength resins like polyether sulfone, or PES. Here is the engineering genius. The PES resin loves to stick to metal, while the PTFE particles love to stick to other PTFE. By blending them, we create a bridge. Inside a clean room environment to prevent dust contamination, automated robotic arms spray a precise layer of this primer onto the rotating pans. The thickness is monitored down to the micrometer, usually hovering around 10 to 15 microns. If it's too thick, it will crack. If it's too thin, the top coat won't have enough to hold on to. The pans then travel through a low-temperature oven to flash off the solvents, leaving behind a tacky, ultra-strong foundation. This layer is the diplomat of the materials world, negotiating a peace treaty between the reactive metal surface and the inner, non-stick top coat. Without this specific chemical cocktail, the non-stick revolution would never have happened. We have the anchor, we have the bridge, now we need the slippery armor. With the primer set, it's time for the star of the show, the PTFE topcoat. This substance is a fluoropolymer, a chain of carbon atoms completely surrounded by fluorine atoms. The bond between carbon and fluorine is one of the strongest in organic chemistry, so strong that it refuses to interact with anything else. This is why it's non-stick. The topcoat is applied in a multi-stage spray process. Robotic nozzles ensure a perfectly even distribution, avoiding any orange peel texture. For premium pans, manufacturers often add reinforcement particles into this layer, such as titanium or diamond dust. These additives don't help with the non-stick, but they act like rebar in concrete, protecting the soft PTFE from being scratched by metal spatulas. By the time the spraying is finished, the pan is covered in a wet, dark liquid that looks like paint, but it's actually a suspended matrix of plastic polymers. It is still fragile and could be wiped away with a finger. To turn this liquid into a permanent, rock-hard shield, we have to subject it to the ultimate test, the sintering oven. The pans now enter a massive conveyor oven, a tunnel of intense heat reaching 400 degrees Celsius, or about 750 degrees Fahrenheit. This is called sintering. It is a delicate balancing act. At this temperature, the PTFE particles begin to melt and fuse together, forming a continuous, non-porous film. If the temperature is too low, the film won't fuse and it will flake off. If it's too high, the PTFE will actually begin to decompose into toxic gases. Precision sensors monitor the oven's atmosphere every second. As the heat peaks, the primer and topcoat layers undergo an interdiffusion process. The polymer chains from different layers tangle together at the boundary, creating a single, unified coating that is now physically part of the pan structure. The metal expands under the heat, allowing the coating to settle deep into those microscopic hooks we created earlier. As the pans exit the oven and cool, the metal shrinks, clamping down on the non-stick coating and locking it in place forever. The bond is complete. The Unbondable has been bonded. Engineering is nothing without verification. Every batch of pans must survive a series of torture tests to ensure the coating won't fail in your kitchen. First is the adhesion test. Technicians use a razor to cut a grid of deep scratches into the coating, then apply a high-strength industrial tape and rip it off. If even a tiny speck of PTFE comes with the tape, the entire batch is scrapped. Next is the abrasion test. A mechanical arm holding a weighted scrub pad or a metal stylus rubs the surface of the pan thousands of times back and forth. This simulates years of cooking and washing in a matter of hours. Then comes the thermal shock. The pan is heated to maximum temperature and then immediately plunged into ice-cold water. The metal and the coating expand and contract at different rates, and the bond must be strong enough to withstand that violent internal stress without peeling. Finally, the fried egg test. Without a drop of oil, an egg is cooked until it's burnt. If it doesn't slide right off with a gentle tilt, the surface isn't smooth enough. Only the survivors make it to the packaging line. The finished non-stick pan is a masterpiece of material science. What started as a piece of dull aluminum and a liquid chemical suspension is now a high-performance tool. We've used mechanical abrasion to create anchors, chemical primers to bridge the gap, and high-temperature sintering to fuse everything into a single slick surface. The engineering doesn't just make cooking easier, it makes it healthier by reducing the need for fats and oils, and it makes cleanup a matter of seconds rather than minutes. But remember, this marvel of engineering is still a delicate balance of physics. Overheating a pan beyond its limit, or using sharp metal tools, can eventually break those microscopic bonds we worked so hard to create. When you see that egg slide effortlessly across the surface, you aren't just seeing a slippery pan. You are seeing the result of decades of engineering research, the successful taming of one of the most stubborn materials on the planet. From the atomic level to the factory floor, this is how we bond the unbondable and bring the power of PTFE to kitchens around the world. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.